right, well, let's get started. We've got a message from Genesis. I believe she wrote it on the board for us. So anyway, everyone is entitled to their own opinion. That's not grammatically correct. Page 502 in your textbooks. Page 502 in your textbooks. Unit numbers 15 to 39. The odd. We're talking about the likelihood of events occurring. The likelihood that... my chalkboard says, anyway, it definitely says seniors rule, so it's highly, perfectly likely, actually. What do we call what's the probability of certainty? Probability of certainty. 1. Probability of impossibilities. 0, and all probabilities lie between 0 and 1. So number 15, when we're determining whether or not that group of probabilities is valid, well, they're only valid if they're all between 0 and 1, but what do all probabilities in a set have to add up to, class? 1. So for number 15, is that a valid group of probabilities, yes or no, Kendall? No, they don't add up to 1. How about number 17, Michael?
Nope.
No, and you could get, just the very first number told you it wasn't, because you can't have a value over 1. What about the next set on number 19, Maddie? Yes, they're all between 0 and 1. They do add up to exactly 1, so that's a valid group of probabilities for a set. Number 21, they wanted the complement. What does complement mean, Abby?
The opposite of whatever's not going to happen.
Okay, the probability of something not happening. So if the probability of event A happening is 0.02 or a 2% chance that it does happen, then the complement of that would be, Abby?
98%.
98% chance it does not happen. Number 23, a certain area had 78 rainy days and 20 snowy days in a given leap year, which has 366 days. If the event is the probability that it will be raining or snowing, what's the complement? Well, what's the probability, first of all, of rain or snow in that particular area? Based on past history, I would say. Audrey?
308. No.
Oh, I wasn't looking for the decimal. I was looking for a ratio. But what's the probability out of 366 days, the probability that it does rain or does snow on a particular day? Right, there's a 98 to 366 chance that it will have rain or snow. So the complement would be the probability it doesn't rain or snow, like we're hoping for field day, praying for field day, juniors. And so what would be the complement, Audrey? She pulls out her calculator in slow motion, dramatically, slowly types in the numbers. 268 to 366, which we could reduce down. What they both divide by at least a 2, maybe more. If you did do a decimal, 0.732, but 268 to 366, whatever that reduces to. Number 25, a particular quarterback completed 315. That's horrible. 315 out of the 798 passes he threw last season. How was he not benched? If the event is the probability that the quarterback will complete a pass, what's the complement? 483 to 798 chance. If you're doing a decimal, 60.5% chance, or 0.605, he does not complete the pass. I mean, you normally want your completion percentage to be higher than that, and that's his incomplete percentage. That's awful. Anyway, I move on. Questions on valid probability sets and complement. Do we feel like we understand those two ideas? Any questions at all on those first several? Let's come to number 27, and it's actually just asking if these outcomes are mutually exclusive or not. It says Tony can buy 3 types of cake, 6 apples, 2 ice cream cones, and a sandwich. What's the probability of him buying a cake or a sandwich? Would that be mutually exclusive or not, Michael?
It is mutually.
Mutually exclusive. A cake is not the same as a sandwich. How about buying a cake, apple, or sandwich, Kendall? Mutually exclusive. Letter C, I don't know if they've corrected it in your book. It says buying a desert item. I guess it's a cactus or a Gila monster or something. Anyway, rattlesnake. Buying a desert item means dessert item. There should be a second S. You caught that, right, Abby? Okay, I was about to say, you caught some things on my last test. You better have caught the dessert thing. Buying a dessert item or an ice cream cone, would that be mutually exclusive or not, Maddie? Not if you consider ice cream cone to be a dessert item, which most people do. If you consider that the main entree, then maybe you would say mutually exclusive. But yeah, so yes, no for the mutual exclusivity on A, B, and C. Questions on 27? 29 car dealers completing paperwork for the following vehicles sold. 3 black cars, 4 red cars, 2 red trucks, 1 blue SUV. Paperwork for a black car or the SUV. What's the verdict there, Audrey?
Mutually exclusive.
They are mutually exclusive. Completing paperwork for a car or a black vehicle. Not mutually exclusive because all the black vehicles are cars. And then completing paperwork for a red vehicle or a truck. Michael?
No.
No, because the trucks were red. Now, it could be a red vehicle that wasn't a truck, but the trucks were red themselves, so that has overlap there. Not mutually exclusive. Questions 27, 29 on the idea of mutual exclusivity. Any questions? All right, dropping down to number 31, finally actually finding probabilities for the first time. We tried to do this one the other day. Marina is checking parking stickers in a parking lot. 54 vehicles are parked, 38 cars, 11 trucks, 4 motorcycles, and a motorhome. What's the probability she checks a motorcycle or a car? Maddie?
5
You got 52 to 54, which reduces down, you said to what?
Oh wait, 7 and 9.
Yeah, 7 to 9 is what it reduces down to. No, 42. Sorry, 42 to 54, which reduces to 7 to 9. Letter B, she checks a motorcycle or a truck. Abby?
5 to 18.
5 to 18. Motorcycle or truck. Sorry, my book doesn't have these answers in there, so I'm trying to do it. Yeah, 15 to 54. Yes, 5 to 18. She checks truck, motorhome, or car. Basically anything but a motorcycle. Audrey?
25 to 27.
25 to 27. Yes, that is what we would get. How many could you go on 31, A, B, and C? Any questions there? Questions? Michael's face says question.
I had 6 to 26.
6 to 26 on letter C?
Yeah.
All right, she checks a truck, which there are 11 of those. A motorhome, there's just the one of those. Or a car. I don't know if you maybe missed where it said or a car. That's probably what happened.
Oh, yeah.
Yeah, or a car, because there were 38. I was going to say that would be 6 to 26 or 3 to 13 if you missed a car, which was on the line underneath. Because all the others are single liners, and that one dropped down under. That's probably what got you. Number 33, Milo has hit 13 homers, 27 doubles, 92 singles, 53 strikeouts, the 185 times he's been to bat this season. What's the probability that the next time he comes up to bat, he'll hit a double or a single? Well, real quick, we're going to talk more about this today. What do we call the likelihood of an event occurring based on past history? Class?
Rational frequency.
Not rational frequency, relative frequency, but you were close. All right, relative frequency, relative to how many times he's been up to bat, how many doubles and singles has he hit? So successful outcomes, in this case successful being double or single, to total outcomes, the 185 times he came to bat. What is that probability? And this is amazing batting average right here. What is that probability for 33A? Abby?
119 to 185.
That sounds right. Plug that into your calculator real quick if you would. Get a decimal. Since batting averages are typically in decimals, I'd like to hear it as a decimal. And she's got
0.643.
0.643, which is, I mean, that would be a great batting average, much less probability of double or single. So again, your ratio initially was
119 to 185.
119 to 185. I don't believe that reduces down, so we'll leave it that way. Letter B, he'll hit a double or a home run. This would be a kind of a slugging percentage. Well, not exactly, but close enough. What did you get for that, Audrey?
8 to 37.
Good, 40 to 185. We can reduce that by 5. You said to get 8 to 47? 8 to 37. Yes, 8 to 37, which would be a 2.216. And then what about a home run, or he'll strike out, or he'll hit a single, which is a really wide range. I'm not sure why strikeouts lumped in there with home runs. But anyway, Brandon?
158 to 185.
Yeah, that sounds right. So 158 to 185 is correct. That'd be 0.854 if you had the decimal there. Questions 31 and 33. How many got all of 33 correct this time? All right.
I did this yesterday too, but I don't see the 185 times, and I just add that. So I was.
Oh, you went. Okay, so you lumped the 185. You added that to all the other numbers. You didn't realize they'd already added it for you. Oh man, that's rough. All right. Let's take a look at number 35. And this time, Michael, they didn't tell you a total. They just said Norman has cards that contain one card of each number 0 through 9. So how many cards does he have, class? 10 cards, right? What's the probability that a 2 or an even number, and they're saying 0 is not an even number, what's the likelihood that a 2 or an even number will be chosen? Well, thoughts on the question, class?
Mutually exclusive.
They're not mutually exclusive. 2 is an even number. So we don't need to do 2 plus the even numbers. If you just do the even numbers, that's going to include 2, right? Mutually exclusive would be like 2 and an odd number, right? But these are not. So how many even numbers are there, class? 4. If they're saying 0 is not even, because it's just a nothing, then that would be 4 to 10 or 2 to 5. 2 to 5 probability. Even number or a prime number. This one's interesting. The probability of even or prime. Well, how many even numbers are there, class, if 0 is not even? 4 out of 10. How many prime numbers? What are our prime numbers, class?
3, 7,
2, 3, 5, 7, 11, 13, 17, 19. But 2, 3, 5, and 7 are prime. So that's 4 prime numbers. Are these mutually exclusive, class? No, because there's one number that fits both bills, and that would be 2. It's the only even prime number, but since there's that overlap, we should subtract that out. We end up getting a probability of 7 to 10. How many got that one? Requires you to remember your prime numbers. What's a prime number anyway, Brandon?
a number that can only be divided by itself for 1.
Right, so again, 2, 3, 5, 7 would be those numbers. 1 is neither prime nor composite because all it has in it is a 1, not 1 and itself. Itself is 1. 4, of course, can be divisible by 2, 6 divisible by 2, 8 divisible by 2, 9 divisible by 3. A 6 or a multiple of 3 will be chosen, and they're saying include the possibility of 3 times 0. What are our multiples of 3 that are in the deck, class? Multiples of 3. 3, 6, 9, but 0 is a multiple of 3 as well. So probability of a multiple of 3 or 6. Well, thoughts on even the question, class? When it's that easy, when 6 is a multiple of 3, so just get the multiples of 3. There's your 4 to 10 or your 2 to 5. So sometimes when you just rule out the second question because it's stupid, you just move on, or the first question in this case because they put the 6 first. Questions on number 35. A little bit more thought into that one, especially on letter B. Are there questions on it? All right, number 37, Lucinda is using a board game spinner, numbered 1 to 6. What's the probability a 4 or an even number will be spun? Stupid question because 4 is an even number. So just find the probability of even. What's the probability of an even number on the spinner, class? 1 to 2, right? 1 out of every 2 numbers is even. 3 out of 6 reduces. A 6 or a multiple of 3. Well, that's stupid too because 6 is a multiple of 3. So how many multiples of 3 are on the spinner? 2. The 3 and the 6. And there's not a 0 on the spinner, so we can't use that. So 2 out of 6 or 1 to 3. A 2 or a prime number. Well, again, if you remember that 2 is prime, stupid question because you just find the prime numbers. How many prime numbers on the spinner? 3. 2, 3, and 5. So 3 to 6 or 1 to 2. So 1 to 2, 1 to 3, 1 to 2, your answers on 37 questions on 37. How many got all 3 of those right? Questions at all? Is it the prime number thing got us? All right. Number 39, a kitchen shelf holds 5 red plates, 6 blue plates, 3 green cups, 8 red cups. We had to find the total ourselves here, Michael. 22. A blue item or a green item is chosen. Well, how many blue items, class?
6.
And green items? 3, so that's a total of 9 out of 22. 9 to 22. Plate or red item. Well, how many plates are there, class? 11 plates. So that's 11 to 22. How many red items are there? 13 red items. But how many items fall into both categories? They're red and they are plates. 5. So we'll subtract the 5 red plates since we had counted them twice. And we end up with 19 to 22. How many had that for letter B? 19 to 22? Okay, just a couple of you questions. Does it make sense now?
I just didn't see the blue plates.
I gotcha. Okay. Cup or blue item is chosen. Well, how many cups are there, class? 11 to 22. And how many blue items are there? 6 to 22. Any overlap between blue and cup? No, there are no blue cups, so we'll just keep it as it is, and we get 17 to 22 is our probability. If you did decimals, 0.409, 0.864, 0.773. Questions on the homework? Feel like we got a better handle on probability after going over it. All right, flip back, if you would, to page 502, and in your notes, I want to revisit this idea of relative frequency with apologies to Genesis. My eraser is not a erasure, rather, it's not an indication of my disagreement with your statement, merely out of necessity to free board space. But I'll leave the 2022 on the sideboard for you. Relative frequency, I believe you have this in your notes already. Do you have it on your formula page? Check your formula page very quickly, if you would, please. Check your formula page. I think I told you to put it on there, but it would have been several days ago. We've had a weekend since then, so I can't promise that I told you. I'm getting a nod from Brandon. Relative frequency is a form of probability. So we're still going to use the letter P for relative frequency. Remember, it's not so much the number of desired outcomes, class, as the number of successful outcomes in the past. Number of past successful outcomes, and not compared to the number of possible outcomes, but the number of total past outcomes. So both of these refer to the past, and that's the key with relative frequency. It looks at what's happened in the past to predict the future. Saying, well, not all odds are necessarily equal. How many times has this person been successful? How many times has success occurred compared to how many total opportunities have there been? Look at number 7 on page 502 and read that, if you would, please, Kendall.
Which number again?
Number 7.
Rachel plays 13 games of chess. She lost 8 games. State the number of successful outcomes for Rachel winning the chess game.
All right, I'm going to deviate from what the problem specifically says. I'm just going to ask, what's the probability that Rachel wins? Well, again, if you're looking pragmatically at it, you would say, well, she could either win, or she could lose, or she could stalemate, which is a tie in chess. Those are the 3 results. So there's a 1 to 3 chance that she wins. Well, no, there's not, because based on past history, she has been successful in winning, how many times, class? 5. She's lost 8 times. She's been successful in winning 5 times. Out of how many games of chess that she played? 13. So her odds of winning are 5 to 13. Slightly better than a 33% chance. That in the stalemate doesn't happen very often. Questions on this? How many chess players in here? So you know what I'm talking about when I say stalemate? You're the only person who knows. Nobody else knows what I'm talking about. All right. It's a game that requires great intellect and strategy and thought and planning. Good reaction. It's great for the brain. Great brain development. It's probably why Brandon's so smart. Number 9. Gerald hit the fairway 243 times out of the 312 times he hit off the tee. What is the probability of Gerald hitting the fairway off the tee? How many golfers in here? Any golfers? No golfers. How many know what a fairway is? How many know what a tee is? It's a little peg thing they stick in the ground with the ball on top of. They hit the ball. Okay, so how many know what the hole is in golf? It's where the ball's supposed to end up by the time you're done. Okay, and the goal is to get it there, hitting it the fewest number of times. And so there's a really smooth area right around the hole. Do we know what that's called? The green. It's called the green because it's green. It's really, really nice. Well, there's also a part that's kind of a path that leads to the green. It's called the fairway. And as long as you hit the ball straight, the ball should go in the fairway. And it's easy to hit the ball from fairway to green to in the hole, right? So the kind of goal is to kind of get it in 4 shots typically, if you're a professional, 3 or less. But then all around the fairway is what they call the rough, because it's rough. The grass is thicker, taller, there might even be weeds, whatever. There's also sand traps, and anyway. So he's able to hit the fairway. As he hits it off the tee, it stays on the fairway 243 times out of the 312 times he hit it. What's the probability? Well, it's not either he does or he doesn't, 1 to 2. Based on past history, he's been pretty successful. What is the relative frequency or the probability that he hits the fairway, class? 243 to 312, right? So the probability of hitting a fairway, now we could reduce it. In fact, if we type that in, fraction 312, and we just hit equals, it'll reduce it down for us to
81 to 104.
There's an 81 to 104 chance. Or if we change that to a decimal, second function, and then the arrow key at the bottom, F to D, it tells us there's a 77.9% chance of him hitting the fairway. That's pretty good odds. He's probably a pretty good golfer. I would not be hitting the fairway that often. I don't think I've ever actually golfed. Like mini golf? Have people mini golf before? It's not nearly the same as real golf, is it? It's just mini. There's nothing wrong with mini, right, Kendall? All right, number 11. In one season, a baseball player hit 30 home runs out of the 412 turns at bat. What's the probability he'll hit a home run when he gets up to bat? That's your seats. Find it as a reduced fraction, and then find it as a percent. 30 homers, he got up to bat 412 times. What's the probability of him hitting a home run? Audrey? First of all, is the ratio? 30 to 412, which we can reduce by 2 to get 15 to 206. And if we make that a percent, what is his percent likelihood of hitting a home run?
7.3.
Good. Rounded to one decimal in the percent, so the third decimal place, 7.3% chance. How many have that? Right? Seem pretty easy? Again, it's not number of desired outcomes to number of possible outcomes here. It's relative frequency, success to past opportunity. Do the same for number 13 there at your seats. Number 13. Basketball player made 204 free throws, and he attempted 261. So game's on the line, he comes to the stripe. What's the probability he makes his free throw, wins the game? I'm trying to remember, it was one of the teams in the NCAA tournament. How many basketball fans, you watch the March Madness? Okay, a couple. I watch March Madness. That's about the only college basketball I watch all year, so I have no clue what I'm doing. I still pick the bracket, and bracket's busted by the first day. It's bad, but I still do it because, you know, it's just what you do. And I was watching one of the games, and the team I was cheering for couldn't buy a free throw at the end of the game. I'm like, what are we doing? Anyway, yeah, it was sad. I didn't win the tournament. I think I was last, actually. Of the people who filled out brackets, there were 3 people who entered and then didn't end up filling out the bracket. I beat all of them. It was bad. Pastor Adam almost won, and then the championship game went against him, and he lost, and he was mad. He was sorely disappointed. It's not spiritual to get mad, and he's a reverend. All right, so what's the probability he makes his next free throw? Brandon?
78.2%.
Yeah, 78.2%. That's not awful. For high school, that's decent. But college, you really want them to be, 85 to 90% or higher. I mean, higher is great too. How many has 78.2% chance he hits his free throw? All right, questions on that? All right, I want you to do numbers 8 through 14, the even. Do 8 through 14, the even. On number 8, find the probability or the relative frequency of jumping less than 15 feet. That's an awkward way to do it. But rather than just the number of outcomes, actually find the probability on number 8. It doesn't tell you to. I'm changing the problem because I think it's stupid. Find the probability that she doesn't hit the 15-foot mark on a jump. Yes. Let your calculator reduce for you. Let your calculator find percents for you.
won't reduce on the 14 because it's too big.
Well, I'll go with a percent then. Or at least divide them both by 2, and then it'll fit, right? So you're like, okay, number 14, you could divide by 2 in your head, and then type that into the calculator, see if it reduces more. Wouldn't be a bad approach. Outsmart the calculator. Michael's got him. Abby's got him. Brandon's got him. Mama Maddie. Miss Kendall. Alright, let's see what we got. Number 8, Candace has long jump. Anyone watch the Olympics?
Who's Candace?
We don't know who Candace is. Anyone watch the Olympics? Does Brandon know who Candace is? Okay. Anyway, Candace has long jumped over 15 feet 42 of the 57 times she's jumped. State the number of successful outcomes for jumping less than 15 feet. Well, how many times did she jump less than 15 feet, class? 15 times, right? So what is the probability that she jumps less than 15 feet on her long jump? Class? 15 to 57 becomes 5 to 19, or as a decimal, what is it?
26.5%.
Right. Questions on that one there? Anyone know what the long jump is? Okay. You sprint as fast as you can. There's a little strip of white. You step on it. Once you step on it, you jump as far as you can to a pit of sand. And you try to not fall backwards. And they measure from the strip to where you might make your first mark in the sand, which is why if you fall backwards, you lose distance. And anyway, 15 feet, it's not a bad jump for a high school girl. Number 10. Baxter was able to hit the bullseye 616 times out of 883 attempts. Now, based on the picture, we're going to assume this is archery. Otherwise, the picture really has no meaning at all. How many shot bow and arrow before? You're actually able to hit the target? You're decent shot with a bow? All right. How many better shot with a gun than you are with a bow? It's usually easier. All right. Anyway, especially with a long gun. Anyway, Baxter was able to hit the bullseye. So with the probability that he hits bullseye and no cows were harmed in the writing of this question, what is the probability? Right, just up front, class.
616 to 833.
Yeah, 616 to 833. As a percent, what would that be, Michael?
I did not do it as a percent.
69.8%.
69.8% bullseye. That sounds pretty good to me. And I don't know, bullseye. That's not like just hitting the target. That's hitting the bullseye. So that sounds pretty good to me. Number 12. Football player caught 83 of the. That's awful. 83 of the 192 passes thrown to him. The real problem is the quarterback throwing him 192 passes and he's not catching them. But what is the probability that he's going to catch the next pass that gets thrown to him? It's pretty lousy odds here. Abby?
43.2%.
83 to the 192, you said was 43.2%. Yeah, that's not very good odds at all. He wouldn't have gotten drafted. Number 14, Maurice sold cars to 402 of the 1,204 customers to whom he spoke. What is the probability, that's an L, that he sells a car to the next customer that comes along? Well, what is the probability as a reduced ratio, class? 201 to 602. That you can plug into the calculator to get the decimal, or you just divide the 402 to 1204 to get
33.4%.
a 33.4% chance of selling a car to the next customer. Pretty much 1 out of every 3 customers, he's getting a sale. Questions on that? How many perfect on all 4? Any questions? All right. Go back and do numbers 1 through 6. So flip back to the previous page. And rather than finding the number of successful outcomes, find the probabilities. I want you to find probabilities. So number 1, Hernando is choosing a random number between numbers 0 through 9. State the number of successful outcomes for choosing an even number. Just what's the probability of an even number? On number 2, what's the probability of a prime number? Number 3, the probability of yellow marble or green marble. That's what we're finding. So find probabilities on 1 through 6. You can leave them as ratios. You don't have to make them percents on these ones. Michael's got them. All right, let's take a look at these together. Number 1, choosing a number between 0 and 9. What's the probability of an even number? Well, if you say 0 is even, 5 to 10 chance. So 1 to 2. If you say 0 is not an even number, it's just a nothing, which is more accurate in my opinion. You say 4 to 10 or 2 to 5. How many have one of those answers for number 1? Again, a couple ways you could look at it. Number 2, Liza's choosing a number between 1 and 20. The probability she chooses a prime number. What are the prime numbers, class? 2, 3, 5, 7, 11, 13, 17, 19, and after that you'd be over 20. So 8 of the 20 numbers. So 8 to 20 reduces down to 2 to 5. 2 to 5. How many had 2 to 5? All right, questions on the prime numbers? All right, number 3, Justin has to pick a marble out of a bag. There are 6 blue, 4 green, 10 yellow marbles. How many total? 20. All right, state the number of successful outcomes for choosing either yellow or green. Well, how many yellow or green are there? 14 out of 20, so a 7 to 10 chance. How many is 7 to 10 for number 3, or 0.7, 70%? Number 4, TJ uses a spinner for a game that can stop, or they can point at the numbers 1 through 6. State the number of successful outcomes for the spinner, or the probability rather, for the spinner stopping on a 5 or a 6. Well, how many numbers is that? It stops at a 5 or a 6. It's 2 numbers out of 6. So 2 to 6 chance, or 1 to 3. How many had 1 to 3 for number 4? Questions. Numero 5. Deck of flashcards contains 4 of each number card. 4 of each number card. State the number of successful outcomes for drawing an even card at random. How many even cards are there, class? 16. 2, 4, 6, 8. But there's 4 of those, because there's 4 2s, there's 4 4s, 4 6s, 4 8s. So that's 16 even numbered cards out of how many in the deck? 36, because there's 4 of each number, 1 through 9, so that's 36, and we reduce it and get 4 to 9. Or you just kind of reduce the fact that there's 4 of everything and say, well, every 9 cards, 4 of them are going to be even, and go straight to this. A couple ways to approach it. How many had 4 to 9 for number 5? Questions? Number 6, player chooses a card for a board game. The deck includes 12 cards labeled A through L. I'm glad they told us that was 12. I didn't have to go A, B, C, D. Say the number of successful outcomes for choosing a C or an F. I want a C or an F. And Andre's like, I'd choose an A, I'm just saying. How many outcomes are wanted, class? 2 desired outcomes out of 12, so 1 to 6. And we had that for number 6. All right, questions on basic probabilities. In some cases, right, the C or an F, 1C plus 1F gives 2 possible that we would want, right? 2 desired outcomes. Same thing with the a 5 or a 6, a yellow or a green. And anytime, class, we see or, we know we need to add. Because what it does is it increases your chances of getting what you want. Does that make sense? By giving yourself, hey, I'm happy with this or this, you increase the likelihood of getting what you want. But imagine if you said, I want this and this. Now you're getting greedy, aren't you? Instead of expanding your horizons, you're demanding more, and the likelihood of getting what you want goes down. We're going to look at another compound probability in your notes. Compound probability involving the word and, meaning the probability that one thing happens, and then, in addition to that, another thing happens. That's going to make the likelihood go down. So compound probability involving the word and. And you need to note this, where with or you add, with and you multiply. When you see the word and, you're going to multiply probabilities. What this does is it decreases the chances of something taking place. Look at page 505, and there's an example that should look somewhat familiar to you. Remember when we first talked about combinations and counting and things like that? We said, well, let's suppose we've got 4 different entrees you could order for lunch, and there's 3 different sides. Well, the odds of a person picking pizza, class, for their entree is 1 to 4. There's a 1 to 4 chance that pizza is picked as the entree. But what about the odds that not only does a person pick pizza, they also choose to have fries with it? Well, again, how many options were there for the side? 3. 3 options of sides, right? So there's a 1 to 3 chance that they pick fries. But when we multiply these 2 possibilities together, 1 to 4 times, because of the and, 1 to 3, class, we get 1 to 12. And the little diagram there shows there are 12 different lunch combinations you could make, right? Hot dogs with apples, hot dogs with french fries, hot dogs with coleslaw. The odds are a 1 in 12 chance that pizza and fries are picked. Does that make sense? What if it had said the odds of a person picking pizza, or as their side they pick fries? Well, then we wouldn't multiply, class, we would add together. Of course, calculator get us the common denominator, all of that. But here's the idea, when you use the word and, you're going to multiply. But there are 2 categories of compound probability. First of all, there's the category of what are called independent compound probabilities. Independent compound probabilities. Does the selection of pizza in any way affect the selection of fries? No. Because you pick any one of these 4 entrees you want, you pick any one of the 4 sides you want. They are completely independent of each other. And for independent, you just take the probability of A and B, and it simply equals the probability of A times the probability of B. For independent events, where the one event does not affect the other, the first does not affect the second. The first choice does not affect the second choice. But there are times where a first choice may affect a second choice. For instance, let's suppose there's a restaurant you're going to pick, and I want to know the probability that you're going to pick this restaurant and you're going to pick this menu item. Well, depending on the restaurant you pick, you may or may not be able to get that menu item. Does that make sense? In that case, the first event affects the second event, and so we would refer to these as being dependent events. Dependent events, where the probability of the first, or the first outcome does affect the second. Notice, by the way, with or, you were still only making one choice. It was either this or that. With and, you're making two choices. Or more. I should say 2 plus. 2 plus choices. You're making multiple choices. And the first does affect subsequent choices. The way we'll find this probability, the probability of A and then B taking place, you'll still start by finding the probability of A, and you'll multiply it by the probability of B given that A has already occurred. The way we're going to read this is the probability of B given A. The most common example of this would be if you're having to make a selection, and a selection removes something off the board. For instance, Wheel of Fortune. Anyone watch Wheel of Fortune where they try to guess the phrase, right? And once a person has chosen, for instance, the letter A, now let's suppose they get A's. Are they going to choose the letter A again? No. Also, depending on where the A's go on the board will affect the choice of letter they make the second time, right? So the first choice does affect the second choice. Let's suppose we had you had your names in a paper bag, and we were going to choose who goes first for oral book reports. And let's see, there's only 6 of you in here. So what's the probability that Brandon gets picked to go first, and then Audrey gets picked to go second? Well, Brandon's only one name out of 6, right? So the probability of Brandon, class, is 1 to 6. But once his name's been chosen, how many names are still in the bag? Only 5. So now what's the probability of Audrey's name being chosen? 1 to 5. She's still one name out of 6, but once one name's been taken out, her odds just got better. She went from a 16% chance to a 20% chance. And the next person's 1 to 4. Anyway, so the odds of Brandon and then Audrey in that order going, class, are 1 to 30. Chance that those would be the first 2 people selected. Does that make sense? One of the things, key word, that you're going to look for in independent versus dependent probabilities is this idea of, well, let's suppose Brandon's name had been chosen, and this wouldn't happen in the case of oral book reports, but Brandon's name goes back in. Maybe we're like, all right, we need somebody to clean the floor. Pick a name. Brandon, you got floor cleaning. We put it back in the bag. Now I need somebody to clean the chalkboard. Brandon. I mean, if we put the name back in the bag, his name could be chosen again, couldn't it? If we replace the first item into the mix again, then at that point, the second event still has a 1 to 6 chance, right? If we were picking, let's suppose Audrey's name came up, but if Brandon's name had been put back in the bag, there's still not only a 1 to 6 chance Audrey's name comes out the second time, right? If we don't replace Brandon's name, which in the case of oral book report is how it works, there's no reason to put his name back in. He can't go first and second, right? I mean, maybe he could. Get 2 shots at it, do better the second time. So what you're looking for with independent, you're looking for the phrase with replacement. With replacement. If you see that phrase, we know we have independent events, and we literally just find both probabilities, no goofy math, we just multiply them together, and it's easy. Dependent events oftentimes will have the phrase without replacement. And if you see without replacement, we know that the first numbers are going to mess up the second numbers. Make sense? For instance, if I'm rolling a die, what is the odds that when I roll a die, a 5 comes up? 1 to 6. So the probability of a 5 is 1 to 6. And then suppose I want to roll a 4 on the next roll. I pick the die up and I roll it again. What's the odds I get a 4, class? 1 to 6. Rolling the 5 the first time doesn't affect the possibility I could get a 4 or a 5, whatever, the next time, right? So in that case, it's in a sense as though the 5 has been replaced. It's still an option. It's still available. Does that make sense? It may not use the phrase with replacement, but we understand the 5 is still available on the second roll. It's just we're not hoping for it. We're hoping for a 4. Again, but if something's removed and not put back into the mix, that's when we'll see the other. Turn to page 506 now, and let's look at some examples in your textbook. Page 506. Let's look at some examples in your textbook. Read with the bold and then the the bold and then the line right under the bold for us. Maddie?
Determine whether or not each pair of events is independent using the given information. John McClure had the following props: 2 trees, 3 bushes, 2 chairs, and 5 clouds.
All right, so letter A, what's the probability of finding a cloud and then a bush with replacement? So there's all these different props up there, and we send a kid who doesn't know what they're doing to go up on stage and grab something. Hey, grab one of those props for me. The kid doesn't even know what he's doing. What's the probability he comes back with a cloud? Class? How many clouds are there? 5 out of how many total things backstage? 12. So the probability of coming out with a cloud is 5 to 12. Then suppose we say, okay, take it back, put it backstage again, then come out with another thing. What's the probability he comes back with a bush? Well, if he puts the cloud back, there's still how many items? 12 items. What's the probability of a bush? 3 to 12. So the probability of cloud and the bush, if he puts the cloud back, because we're like, we don't really want that, put it back. Now, again, this assumes the kid has no intellect whatsoever. And he can bring a cloud out, we say we don't want it, he puts it back and comes back with a cloud again. Okay, probably not the case, but theoretically at least, 5 to 12 times 3 to 12, we could do a little reducing here maybe. Notice with multiplication, with and, reducing is beneficial because we don't need a common denominator, do we? For or problems where we add, we want that common denominator. Here I don't care. And so when we multiply, we get 5 to 48 chance of cloud, then bush. Letter B, finding a chair and then a tree without replacement. Kid goes backstage, brings out a chair. What's the odds, looking at the problem, he comes back with a chair on the first time?
1 to 6.
There's 2 chairs, right? So that's a 1 to 6 chance that he comes back with a chair. But if he doesn't replace the tree, or if he doesn't replace the chair, what's the odds he comes back with a tree? Well, how many trees are there? 2 out of how many props now?
11.
Only 11. There's a 2 to now 11 chance of a tree coming out. Does that make sense? Because we took one of the 12 props and we kept it. We didn't replace it back. We do a little bit of reducing, by the way.
1 and 3.
And so what's the odds? He comes out with a chair and then he comes out with a tree.
1 to 33.
1 to 33 chance. Again, a little absurd, but whatever. Questions on the idea of independent versus dependent. And again, a lot of times you'll see those phrases with replacement, which means the first thing's not going to mess anything up if we replace it anyway. Without replacement, the first thing is definitely going to mess things up for the second one. Look at the next example problem. On page 506 at the bottom now. 8 marbles are hidden in a bag. 4 red, 3 blue, 1 yellow. What's the probability of selecting 2 consecutive blue marbles with replacement? Meaning, we reach in the bag, we feel around, we pull out, hey, it's blue! We drop it back in. Feel around for a minute. That doesn't mean we keep it in our fingers while we swirl around. We actually drop it, reach back in, swirl around, hey, it's blue again! Well, what's the probability of a blue the first time, class? 3 to 8. What's the probability, if we drop it back in, of getting another blue? 3 to 8. And we just multiply, neither of those reduces, so we get?
9 to 64.
There's a 9 to 64 chance that we pull out a blue, drop it back in, grab another blue. Make sense? But what about, I think we're wanting to take a look at, nope, we're not, I'll go with it myself. What about if we don't put the blue back in? The first time we draw, there's still a 3 to 8 chance of a blue, right? We reach it, hey, it's blue! Set it aside. How many are in the bag? 2 blue out of 7. So do we see how the first has affected the second? I can even do a little reducing, by the way.
1 and 4.
What's the odds of back-to-back blues if we don't replace? 3 to 28 chance if we don't replace the first blue. Questions on that? Starting to see the difference between dependent and independent. All right, this is more tomorrow's concept. In fact, we're out of time, so we will stop there. Homework for this evening has nothing to do with the and. Okay, so the homework tonight doesn't involve the and scenario. We're going to work on that more tomorrow before we do any more work with it on your own. I do want you to do pages 502 to 503, pages 502 to 503, numbers 16, 18, 20, 28, 30, so 5 problems, 16, 18, 20, 2830. And then on pages 511 to 512, pages 511 to 512, do numbers 5 through 14. It's in the review section. Pages 511 to 512, 5 through 14 in the review section. We'll take a look at that tomorrow. Have a wonderful rest of your day.